This video will be an introduction to sequences. In this video, you will learn what is a sequence. You will learn what it is for what it means for a sequence to converge, and you'll learn some basic patterns for finding sequences that will be useful in the future. All right, the first thing, what is a sequence? Well, a sequence is sort of like what it sounds like. It's a sequential list, and so the mathematical definition is a sequence is a list of numbers. Some might even call this list of numbers a function. In fact, a sequence is a special type of function. And it's a list of numbers that can be basically matched up with the natural numbers. And the natural numbers usually are denoted with lowercase n, and these are just 1, 2, 3, 4, the basic counting numbers. For example, I could have the sequence a sub n, and we use braces to usually define sequences. And this could be the sequence 1, 2, 4, 8, 16, etc. You might notice a pattern. These are all powers of 2, and so we could say that this a sub n equals 2 to the n. And so you can see that this n denotes the exponent, basically. And you do have to be careful. I did mess up a little bit. The n always starts at 1 for a sequence unless otherwise specified. So this is n equals 1, n equals 2, etc. So for this pattern to work out, this is actually 2 to the n minus 1. So that's something that you might have caught. If not, you need to be aware that sequences start at n equals 1 unless specified by something else. Let's examine the sequence a little bit further. Notice that the numbers 32, 64, etc., they get bigger and bigger and bigger. And actually, there is no upper bound to this sequence. If we were, for example, to take the limit as n approached infinity of this sequence to the n minus 1, we would find that it would be infinite and just go on forever because 2 to the infinity is infinity. And we call this is a divergent sequence. The sequence diverges, and it diverges because it does not go to a single number. Let's say that instead that we had a different sequence, a sub n equals 1, 1 half, 1 fourth, 1 eighth, etc. And so this is basically the opposite, and we could write this sequence as a sub n equals 1 divided by 2 to the n minus 1. Notice that these numbers get smaller and smaller and smaller. If we were to graph them, we have like 1, a half, a fourth, an eighth, a 16th, etc. These numbers trend towards 0, and mathematically we can check that by taking the limit as n goes to infinity of 1 over 2 to the n minus 1. Clearly, this is going to go to 0 because 1 over infinity is 0. And this is an example of a series that converges because the limit goes to a single number. Let's take a look at this series. A sub n equals 1, negative 1, 1, negative 1, 1, etc. If we were to graph this, notice that the points just kind of alternate between negative 1 and 1, etc., like this. This series does not go towards a single number at infinity. And in fact, it goes to two separate numbers because you could pick out this series, or like a subsequence, for example, that goes to 1, and this subsequence that would go to negative 1. So this, so this 1, negative 1, this alternating series diverges, it does not converge, because it does not go to a single number. So do all alternating series diverge? No, because you could have something like this. You could have 1, negative 1 half, positive 1 third, negative 1 fourth, positive 1 fifth, etc. And so this sequence would look like this if you were to graph it. You'd start at 1, negative 1 half, positive 1 third, negative 1 fourth, 1 fifth, etc. And this sequence would alternate, but it would slowly approach 0 as n grew to infinity. And so this is a series, this sequence would converge, and in fact the sequence here converges to 0. Part of getting good at sequences is to recognize patterns. Let's say that we had the example of 1 comma, nope, we'll do a half. 1 half, 3 fourths, 7 eighths, 15 sixteenths, 31 32nds, etc. Now you might be able to notice a pattern. Ooh, that's interesting. Notice that the bottom is a power of 2 each time. And so my general term, I could say this is divided by 2 to the n, because I'm doing 2 to the first, 2 squared, 2 to the third, 2 to the fourth, etc. And the top pattern is that, oh, it's always 1, or it's the bottom term minus 1. And so that would be 2 to the n, or actually I'll write it in red, 2 to the n, and then minus 1. So this is a good way to get good at identifying what the patterns are. If I take the limit to infinity, notice you can see that these are getting closer and closer to 1. And in fact, if I do L'Hopital's rule on this, I'll get 2 over n over 2 to the n. This will go to 1 as n approaches infinity. Let's say as a separate pattern, I have 1, 2/3, 3/5, 4/7. The next one would be 5 over 3, 5, 7. That would be 9. These are all odd numbers. So the top pattern, you have the first one is n is 1, n is 2, n is 3. You always want to find the pattern relative to those numbers. So the top is basically just n, because these always match the n value. And then the bottom is always the odd numbers. And for odd numbers, you have to be a little bit clever. Notice that here, it's 2 goes with 3, 3 goes with 5. And if you were to double this, you would get 4, or let's think of it rather as 2 times 2 minus 1. This one is 2 times 3 minus 1. 7 is 2 times 4 minus 1. 9 is 2 times 5 minus 1. So in general, odd numbers are going to be 2n, and then either plus or minus, depending upon what thing you're starting at. In this case, it's minus 1. So that would be the pattern there. As n approached infinity for this sequence, what would happen would be, well, the 1 really doesn't matter anymore, and you'd essentially end up with 1/2 using Bobo-Botten or L'Hopital's rule, so you get 1/2. A favorite type of series or a sequence that we'll run into later is one that alternates. So 1, negative 1/2, positive 1/3, negative 1/4, positive 1/5, etc. Notice here that to get the fraction part, we just do 1 over n. That's pretty simple. But to get it alternating, you kind of have to be a little bit clever. And the way we're going to be clever to get things to alternate is to do negative 1 to the n. This is going to get us an alternating series. However, we need to either keep it as n or do n plus 1 depending upon the first term. Notice here that this is n equals 1. And so if I use my formula, negative 1 to the 1 times 1 over 1, I would get negative 1. I don't want that. So what I have to do is I have to add 1 to the exponent on the negative 1 in order to make this a positive. And so my formula ends up being negative 1 to the n plus 1 times 1 over n. So just remember that if you see a negative 1 to an exponent, this is going to make it alternate. And you get something called an alternating sequence. The last number pattern that we're going to look at is one that you may have seen before, but you might not have. It goes 1, 2, 6, 24, 120, 720, and so on. And maybe you've seen these numbers, maybe you haven't, but if you haven't, you're going to learn to love these numbers. Here's the pattern. We start with 1, and then to get to the next one, we multiply by 2. Then we multiply by 3. Then we multiply by 4, by 5, etc. And so what we get is the sequence 1, 1 times 2, comma, 1 times 2 times 3, comma, 1 times 2 times 3 times 4, comma, 1 times 2 times 3 times 4 times 5, etc. This gets really long and boring to write after a long time, and so the way that we denote this is with the very exciting symbol, da-da-da-da. This is called a factorial. And a factorial is just an easy way to condense the notation that we just did. So for example, 3 factorial is you start with a number, 3, and then you just subtract 1 until you get down to 1. So 3 factorial is 3 times 2 times 1, which is 6. If we go back to this original sequence, we basically have 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, etc. the basic term here is n factorial. So you have that. And just a special note, 0 factorial is not 0. 0 factorial is defined to be 1, and we'll see why when we get later on into sequences and series, but 0 factorial is defined to be 1 to make things work out more nicely.